All right, 2.1, derivative. The derivative notation can be written as follows: f prime of x, dy by dx, and y prime. Now, specifically, that dy by dx is something used very often. That's known as Leibniz notation, and I'll write that in a little bit. The derivative of a function is a formula for finding the slope of the tangent at a particular point. We use the same formulas as in the last chapter, except not at a particular value. And again, dy by dx is known as Leibniz notation. And you will be asked sometimes to find the derivative using Leibniz notation, which is known as dy by dx. Or if you're given the function f at x, it would be known as df by dx, and it would be df at x. So df at x by dx. That is known as Leibniz notation. All right, now the limit as h approaches 0 of f at x plus h minus f at x all over h. That's what we used in the last unit, and that basically is to find the derivative. Now, in example A, given f at x equals 3x squared plus 2x, calculate f prime at x from first principles. What is first principles, folks? Well, that is that limit function that you see above there. That is known as first principles. So if I ask you to find the derivative using first principles, that'll be the same method that you used in Unit 1 in Chapter 1. All right, now we need to find the derivative. Take the limit of the function and divide it by h. We expand it, and that equals the derivative. Expand it, collect like terms, factor for h, and the h's cancel, and you get f prime of x is equal to 6x plus 2. 6x plus 2 is the derivative of f at x in the original function. All right, part B. Calculate f prime at 4. So from part A, we found that f prime of x is equal to 6x plus 2. That's the general equation. F prime at 4 means we plug in x at 4, and we get 26. All right, example number 2. Given y equals x plus 3 over x minus 1, calculate y prime from first principles. How do we do that? Well, same thing that we did earlier, use the limit. So y prime is equal to the limit as h approaches 0 of the function. And first step is to find the common denominator. Once you find the common denominator, expand it, collect like terms. That's, again, all of that is the denominator. And that's, so common denominator, which means the numerator, as we see over here. All of this is the numerator right here, folks. All of this is that numerator expanded. That would be x plus h plus 3 times x minus 1. That gives us all of this. And x plus 3 times x plus h minus 1. And that gives us all of this. There's a minus here. That would be this minus right there. So that's why you have the big brackets. In the denominator, that would still be this h, and the common denominator of the denominator is in the bottom of the original numerator. And what happens here is things start to cancel. X squareds cancel, the hx's cancel, the 3x cancels, the minus x cancels, and the minus 3 cancels. So that you're left with minus 4h all over h times x minus 1 times x plus h minus 1. Now, where did that 4h come from? I'll just show you here. Here's the minus h don't forget that there's a minus here of this 3h. So minus h minus 3h gives us minus 4h. On the bottom, we still have all of this. So that means that this h and this h will cancel each other out. And you're left with the limit as h approaches 0. Well, we can apply the limit, folks, and we end up with y prime is equal to this function right here, negative 4 x minus 1 all squared. That is the derivative of the original function, rational function up here. All right, next question. A function is differentiable at a point x equals a if f prime at a exists. For example, f prime at a does not, but f prime at a does not always exist. So, for example number 3, show that the absolute of x plus 2 is not differentiable at x equals 0. So let's find out why. Well, if you remember, an absolute function is known as a piecewise function. So you need to have two pieces for the absolute. One is when the absolute number inside is negative. In order to make a negative positive, you have to multiply that negative number by a negative sign, negative 1. If that number inside here is positive, then the value stays the same. So that's why you'll have x plus 2 as our other option. So there are conditions. When does it equal this? Well, it equals this when this value is negative. So we say if x is belonging to that interval. And it's x plus 2 if x belongs to the interval from 0 to infinity. So positive value. So we're going to use first principles because we know no other way to be able to find the limits. So take the limit of the first one. That would be the first one right up here. We're finding the derivative of the top one using first principles. And that's the derivative we're trying to find. And we get a value of the derivative being negative 1. Now, we find the derivative again of the second one, which would be this one. And we find that the derivative of that is going to be, after we calculate it, will be positive 1. Well, folks, if you have the derivative of one being this value and the derivative of the other one being this value, they're not the same. And because these two derivatives are not equal, it is not differentiable at this, it's discontinuous. Therefore, it's not differentiable. So, since the limits are not the same, y equals absolute of x plus 2 is not differentiable around x equals 0. Now, let's look at graph derivatives. The best thing here, okay, what we did here is we looked at things from your textbook. But let's go back a step, just a little bit. So you have to note that in that last question, this one over here, because these two values were not the same, so these two values here were not the same. They're not the same. Therefore, this is the condition at where it changes the 0. This function is not differentiable because the values are not the same. So now we could find out at point A, if I put a 0 here, this value will be this, if I put a 0 in here, I get a value of 2. If I put in 0 here, I get a value of 2. So the point exists. But the problem is the derivatives have different values. Therefore, since the derivatives are different values, it means that f prime at a does not always exist because the derivative has to be the same. So, and it has to be the same as it approaches both levels. All right, last little bit. Let's look at graphs. We're looking at graph derivatives. Now, very important, if you're given a function f at x, you sketch the derivative, okay, by plotting all max and min points as zeros. You plot them on the x-axis. plot above the x-axis for positive slopes and below the x-axis for negative slopes. So let's look at an example here. This is an example from the book. So what we did here is we tried to match all of these values. Looking at the first one, part A, we need to see what happened in part A. Well, look at A. It has a max at 0. So that means the graph must go through 0, 0. And what happens is to the right of this graph, you see to the right of this graph, the slopes are increasing. So that means the slopes would be positive. The slopes are positive means that the graph has to hit 0, 0, and on one side all the slopes have to be above the x-axis. On this side the slopes are negative, and because they're negative, what happens is that everything beyond 0, 0 must be below the x-axis. Which graph does that match? Well, you should see that A matches with E, because it goes through 0, 0, just like I said. To the right of it, it is all negative. The slopes are negative. To the left of it, the slopes are all positive. And that's what was happening here to come to here. All right, let's look at B. What's happening with B? This is one that tends to be tricky. If you don't want to do B, we could look at C. Let's look at C if you want. B and C have different things going on. In C, we have a minimum at -2, a maximum at 0, and a minimum at 2. So these should be all the zeros at -2, 0, and +2. This is the only one that has 3 zeros right there. So you should have seen that this matches with this. And B then automatically matches with F. Why is that the case? Well, we could also look at the slopes to see what's going on there. Notice here that the slopes of all the slopes going across, all the way across here, the slopes are constantly positive. Positive, 0 slope here, and positive again. So what's happening here is the slopes are positive, 0, and positive again. What's the only graph that has all positive slopes? Well, here, right here, positive, 0, and positive again. So that makes sense that B matches with F and C matches with D. So B will match with F, C will match with D. All right, folks, hopefully that makes sense. We'll talk more about this. Take care. Have a good night.